Use the form of the definition of the integral to evaluate the integral. So let's go ahead and express this integral using the definition, which says this integral equals the limit as n approaches infinity of the sum when I equals 1 to n of f of x sub I times delta x. Now let's look for our specific integral. We're looking from 0 to 2, so we could compute delta x. That's going to be 2 minus 0 over n, which is 2 over n. So our x sub i's, our intervals, are going to be 2 over n I, and the function value there. Let's put all of that together then with our function here, and we have the limit as n approaches infinity of the sum as I goes from 1 to n. So we've got our function putting in 2n over I, so that's going to be 2 over ni minus 2 over ni cubed, and that's multiplied by delta x, which is 2 over n. Now looking at this summation just involves I, so we can move anything that involves an n out in front, and we can also use the properties of summation to move constants in front and also to look at this subtraction and take the summation of each piece of that. So what that's going to leave us is the limit as n goes to infinity. Looking at this piece, we could put 4 over n out in front and then leave our summation I equal 1 to n, and we have the I. Then we can subtract, and this would be 8n cubed. We can move that out in front, and then we have the summation I equal 1 to n of I cubed, and then I see, oops, I still have this 2n that I didn't write here, and so let's move that out in front as well, and so I'm just going to put that right here, 2 over n. Now we have the formulas. We have a formula for this particular summation, and we also have one for this particular summation. I'm going to list those. Let's look. We were given I equals 1 to n, summing up I. That equals n times n plus 1 over 2. And we also have the sum as I goes from 1 to n of I cubed, and that one was n times n plus 1 over 2, the quantity squared. So we can replace both of those summations with that, and let's write down what we've got. So we have the limit as n approaches infinity. This is going to be 8 over n squared, and then replacing that summation, and I'm going to go ahead and distribute this through as well. So n squared plus n over 2, and then minus 16 over n to the 4th, because we still have that 2n that applied right here, and then replacing that summation with the formula, that's going to be n times n plus 1 over 2 squared. Okay, let's see what we can do with that. We've got the limit as n approaches infinity of, we can reduce here and get 4, and then as we apply this n squared in the denominator, this looks like that's going to be 1 plus 1 over n, and then we have minus, and if we squared this 2, it would become a 4 that we could reduce with this 16, and so we would have a 4. And let's take this n to the 4th and move it inside of the squared, put it right here, so n squared squared, because we can see that this would be n squared that we could apply that to, which would make that a 1 minus, and this would be an n over n squared, so that would make that a 1 over n. Now we are ready to take the limit as n approaches infinity. So we see that would go to 0 and that would go to 0. And it looks like we would have 4 minus 4, which is 0. Now it's like, wait a minute, we did all this work and all this summing and everything canceled out and this gave us 0. So when we compute this integral, we are looking from 0 to 2. And we were looking at, we have the area here, a sub 1. We have an area over here that's below the x-axis, a sub 2. So when we compute the integral, it's going to be a sub 1 minus a sub 2. So this area obviously equals this area, and we ended up with an integral value of 0.